My name is David Liu, and today I'll be presenting on behalf of my co-authors our paper titled Group Fairness Without Demographics Using Social Networks. So traditionally, group fairness definitions rely on access to a sensitive attribute label, such as sex or race. In order to define groups, we would like to balance outcomes and risks. However, oftentimes these labels are either unavailable to us or even harmful to them. So in this paper, we ask if we instead have access to a social network, is it possible to measure group fairness? Now, we also add the criteria due to privacy reasons of avoiding either partitioning this network or recovering the sensitive attribute at any point in the process. So accordingly, our contributions are as follows. First, we introduce a measure of group fairness that does not depend on group labels. Instead, it uses homophily in social networks to reduce inequality. Second, our approach is group-free in that it avoids attempting to define groups entirely. It is solely based on the similarities between individuals. Last, we theoretically analyze our measure and show that for 3 real-world tasks, it is able to be used to reduce the inequality between groups. Now, before going any further, let's review the concept of homophily, which is the tendency of individuals to connect at a higher rate with individuals they are similar with, or the common saying that birds of a feather flock together. In the social sciences, this is widely observed across many attributes, such as the ones shown here, in types of connection. Now, our approach of group-free group fairness leverages homophily. The center of our approach is this kernel K inferred from a network, which captures the similarities between every pair of individuals in the population. We also have a vector Y, which is the vector of individual outcomes for which we would like to balance amongst groups. Now, our measure of group-free group fairness is this expression in red here, which has 2 key parts. The first one is an averaging function, which takes the kernel in the individual outcomes and smooths the outcomes according to the kernel. Second, we have a function f, which is an economic inequality measure. An example of one is normalized variance. Now, to put these pieces together, let's look at a toy example for intuition. Say we have a kernel K inferred from a network that has clear block structure. Now we also have an outcome vector Y, and if we feed both of these into the averaging function, we can see that the smoothed values reflect the fact that the upper block has a higher average of outcomes than the lower block. Of course, for a general network, this kernel K could have more general structure. Nonetheless, this example captures the intuition of the smoothed values. Now, this begs the question how we infer the kernel from the network. We acknowledge there's many ways to do this, and we present one method in the paper, which starts by embedding all the nodes in the network into a low-dimensional space using, say, Laplacian eigenmaps. We can then define the similarity between individuals by taking, say, the cosine similarity between their embedding. And last, the kernel K is simply the column normalized version of the similarity matrix. On the right-hand side, you can see examples of the similarity matrix or kernel matrix in action, where we have synthetic stochastic block models and the corresponding kernel matrix, which reflects the planted community structure we expect. We also theoretically analyze this measure and show that it is commensurate with the property of additive decomposability. From the economic inequality literature, a function f is additively decomposable if given groups. The total inequality is precisely the inequality within groups added with the inequality that is between groups. In our paper, we show that for an inequality function f that is additively decomposable, given a kernel K, it must also satisfy this expression below. where the right-hand term is not only our measure of free group fairness, it is also the inequality between groups. I'll also take this time to add the fact that while individual fairness definitions also use similarities between individuals, it's important to acknowledge that our method is different. In fact, by reducing inequality among smooth values, we're actually ensuring that different individuals, or dissimilar ones, have similar outcomes. So let's move to some empirical evaluations. Across the board, we use data sets that provide not only a social network, but also the ground truth sensitive attributes. We only use the sensitive attribute at test time to ensure that the inequality amongst the known groups is actually reduced. And we compare against a naive baseline of community detection, where the kernel is constructed by taking communities inferred from the network. This violates our initial criteria of not partitioning the network, but it is nonetheless a naive baseline to compare against. So our first task is node classification, where the setup is that we have a classifier that labels nodes 0 or 1, and 1 is the desired outcome. Our task is to post-process these labels and relabel them so that for the smoothed values, all entries are above a minimum threshold. We can see on the right for two real-world networks, Poblogs and the email network, as we increase this threshold, the desired outcome is more and more evenly dispersed throughout the network. Next, we tackle a perhaps more involved example of maximizing information access. The goal here is to maximize the reach of a helpful piece of information, which starts at a seed node set and then cascades through the network. And our task is to choose which nodes to add to the seed set. Our algorithm greedily selects nodes that maximize the minimum value of the smooth vector. And we compare against other baselines that greedily maximize total reach, the minimum individual exposure, or the minimum community exposure. And on the y-axis, we have evaluation using the ground truth sensitive attributes and show the inequality between the known groups following the cascades. And we can see that for many configurations of graphs and seed budgets, our algorithm yields the lowest ground truth inequality amongst the groups. Last, we look at the setting of recommender systems. Here we consider a world where we have a set of items, and for every user, we have their ratings over these items. And our task is to provide a ranking of all the items for every user. And we would like to balance on one hand user utility or the user's enjoyment of their highly ranked items, as well as group fairness for users, where for a given item, we would like to make sure it is recommended or exposed to all groups of users, preventing a setting where a given item is recommended only to a subset of groups. And we can achieve this by optimizing a joint objective where each algorithm yields a different trade-off curve between the two objectives. And we can see in the plots below that our approach outperforms the baseline in which we treat all users individually and balance exposures of items in that manner. However, we underperform compared to the ideal scenario in which we have the actual sensitive attributes, which is to be expected. So to conclude, a few limitations to acknowledge are that in the real world, network datasets can be biased in how they are collected and sampled. Further, the network we used must have discernible community structure. We are also assuming the network is formed due to homophily. And last, the embedding process to construct the kernel may require multiple rounds of tuning. Nonetheless, we present a group-free measure of group fairness based only on similarities and show that for real-world tasks, it is able to reduce inequality between groups while avoiding partitioning the network. Thank you for listening to this talk, and you can see the full details in our paper here.